Hello, today we're continuing with our GCSE physics revision series looking at Ohm's Law, V equals IR. Last time we looked at static electricity, where electrons simply sit on insulators because they cannot move through them. Today we're going to be looking at electrons that move through conductors. Conductors allow the passage of electrons, insulators do not. So we have electrons in something like a wire, say a copper wire, that are moving. In order to move, they need to be, as it were, attracted. So there needs to be, as it were, a positive terminal and a negative terminal. And electrons which are negatively charged will be attracted to the positive terminal. We'll see more how that works a little later on. But think about a battery. A battery has a positive and negative terminals, and the electrons, when they go round an electric circuit, are going towards the positive terminal. So here's a very basic circuit. We start off with a battery, which we represent schematically like this. The longer end is the positive side, the shorter end is the negative side. And we go through what we call resistance, R, and back the other way to complete the circuit. The circuit always has to be complete, otherwise the electrons cannot flow. And the current flows in that direction. Now I immediately expect to hear you say, wait a minute, you told us that electrons are the current and electrons are attracted to the positive side, which means the electrons are travelling this way round the circuit. Why have you put the arrow in that direction? Well, this is all to do with history. You see, electricity was discovered long before electrons were discovered. So people knew about electricity, but they didn't know how it worked. And they assumed that whatever it was that was flowing must flow from plus to minus, because it seemed to make sense. It was only when we discovered the electron and found that it was negatively charged that we now know that it's the electrons that flow, and they flow to the positive terminal. Nonetheless, the old history remains, and we still put what's called the conventional current as going from plus to minus. Actually, of course, nothing flows from plus to minus. The electrons flow from minus to plus. Nevertheless, because of history, we show the current as flowing, and we call it the conventional current because conventionally that's what they called it, as flowing from plus to minus. What is a resistance? Well, again, we'll come to that a little later on, but in essence, a resistance is something which conducts electricity, otherwise the electrons couldn't pass through it, but it impedes them. So it, in a sense, restricts their movement. And if it restricts their movement, it restricts the current that can flow. So we've got a battery that will have a voltage, we've got a current, which we call I, and we've got a resistance R. Let's just rehearse what each of those are for. V is for the voltage, sometimes called the potential difference or the potential drop, and that is measured in volts. I is for the current, which is the flow of electrons around the circuit, and that is measured in amps. R is the resistance, which impedes the flow of electrons but doesn't stop them altogether, and that is measured in ohms, or the Greek letter omega. And Ohm's law very simply says that V equals IR. Now we'll see later that that is not always the case, but for the time being we're going to stick with Ohm's law, V equals IR. So the voltage is equal to the product of the current times the resistance. So let's suppose that we've got a 9-volt battery, and let's suppose that the resistance is 3 ohms. What then is the current that is flowing? Well, if V equals IR, we can rearrange that to say that I is equal to V divided by R. You need to be able to manipulate these equations. They're not difficult. You just have to divide both sides by R. So V equals IR gives you that I is V divided by R. And now you just substitute. V, you'll remember, was 9 volts. R was 3 ohms, so it's 9 divided by 3 is 3. and the units are amps. So the current flowing in that circuit will be 3 amps. Let's just think a little bit more about resistance. Why should there be a resistance to the flow of electrons? Well, we'll consider a wire. And what we're saying is that the electrons in that wire are moving in that direction because that's where the positive charge is. So they are attracted to the positive charge. But this wire is full of atoms. And those atoms aren't just sitting still either. Atoms that have any kind of temperature will be vibrating a little so that each of these atoms is moving about a bit. And that's going to hinder the flow of the electrons. Obviously, the longer the wire is, the further the electrons have got to travel through. So as the length increases, the resistance increases. But the cross-sectional area goes the other way round. It's rather like a corridor. The wider the corridor, the less resistance there is. So the greater the cross-sectional area, the less the resistance. And finally, of course, it also depends on the substance itself. What is the substance made up of? And that's called its resistivity. Every substance has a particular resistivity, which determines the extent to which it impedes the flow of electrons. And the resistance of any resistor is a combination of the resistivity, that's the basic makeup of the material you're using, the length of the resistor, and the cross-sectional area. How are we going to measure current and voltage? Well, let's draw exactly the same diagram that we drew before. Here we've got the battery. We want to know what current is flowing. I mark it again as a conventional current. We want to know what current is flowing, so we use a device called an ammeter. An ammeter is just an electrical device that has a scale on it, and it measures the amount of current that's flowing through it. So the ammeter is put in the circuit. Here is the resistance, R, and then we need to complete the circuit. And we want to know what is the voltage across that resistance. So we put the voltmeter across the resistance. And a voltmeter is another piece of electrical equipment that has a scale on it, and it reads the voltage, or sometimes called the potential difference, across the resistance. It's no use putting the voltmeter up here because that isn't measuring anything. Well, it will measure something, but not what you want. You want to measure the voltage across the resistance because that's the current is going through the resistance, and you want to know what the voltage across that resistance is. So that's a good circuit for measuring the voltage across the resistance and the current flowing through the resistance. I said that we could think of voltage as potential difference. And we could think of this in terms of, let's say, water flow. Let's suppose we have a tube like this. And suppose we have the water level on either side exactly the same. Well, there is no potential difference between the two sides, so you won't be surprised to know that no water flows. It just sits there, nothing happens. But suppose instead we have a situation where, with a combination of taps that can restrict where the water can move, we have water at that level on this side, but at that level on this side. So this is the water, and we've got taps to stop it from moving. Now you'll notice that we've got a difference in height. That is called a potential difference. And what will happen if we undo the taps so that now the water can flow? The water will flow in this direction, and it will continue to flow until both sides are at the same level. In other words, until there is no potential difference. So the potential difference is what, as it were, drives the water. And exactly the same thing happens with a battery. A battery provides a potential difference. What it says is that this side of the battery is, say, at 9 volts, but this side of the battery is at 0 volts. That's the equivalent of having a high level of water on this side and a low level of water on this side, and that causes a current to flow until, of course, the battery is spent, in which case there will be no potential difference. You'll have used it all up. Now let's think what we mean by current. I've just told you that current is essentially electrons flowing in a wire. They are moving towards the positive end of the battery. They are negatively charged. So these are lots of negative charges that are moving. And the definition of current, I, is the amount of charge divided by the time in which that charge flows. That is the definition of current. So let's take an example. Say we have a charger. We're recharging our car battery and the charger delivers 2 amps for 2 hours. What is the total charge that is put on that car battery? Well, if I equals Q over T, then rearranging that formula, you get that Q is equal to I times T. So the amount of charge on the battery will be the current, which is 2 amps, times the time. Remember, time has to be in seconds, so don't get trapped here. That's 2 hours, but each hour has 3,600 seconds. So 2 times 2 is 4, times 3,600 is 14,400, and the unit of charge is a coulomb. So you put 14,400 coulombs of charge on the battery if there is 2 amps flowing for 2 hours. Now let's think a little bit more about what this thing called voltage is. Here's the battery, which has the voltage, and here's the resistor. And we know that a current, the resistor R, the voltage V, current I. We know that Ohm's law says that V equals IR. Now, what is that battery actually doing? What it's actually doing is driving the electrons round the circuit. It is doing work. It is providing energy. And that's the definition of voltage. Voltage, sometimes called potential difference, is the work done to move charges around the circuit. So it is work divided by charge. It's the energy transferred per unit of charge. So we've now got 3 equations. We've got Ohm's law, V equals IR. We've got the definition of current as being the amount of charge moved per unit time, charge divided by time. And we've got the definition of voltage, or potential difference, as being the work done to move a particular charge. So those are the 3 key equations that I'm now going to use in a test question. So once again, I'm going to draw what should now become a familiar diagram: a battery, a resistance. The battery has a voltage V. There will be a current flowing. I can tell you that the voltage is 1.8 volts, and I can tell you that the current that flows is 0.3 amps. And there are several parts to this question. The first is, what is the resistance R? For that you need Ohm's law. V equals IR. That means that R is going to be V divided by I, which is 1.8 divided by 0.3, and that's 6 ohms. The measure of resistance is ohms. So that's the first part. What's the resistance? The second part is that the current flows for 20 seconds. I have a switch in the circuit, say, and I let the current flow for 20 seconds. And the second part of the question is, what is the charge that flows through the resistor? Well, now I'm going to need the equation I equals Q over T, which means that Q is equal to I times T. So the charge is equal to the current, which is 0.3 amps, times the time, which is 20 seconds, and seconds is okay, and 0.3 times 20 is 6, and it's the charge we're calculating, so that will be 6 coulombs. So 6 coulombs of charge passes through the resistance in 20 seconds. And the final question is, what is the work done by the battery to drive that charge through the circuit? And once again, we remember that the definition of voltage is the work done per unit charge. And so consequently, that gives us that the work is equal to the voltage times the charge. The voltage is 1.8 volts. So that's 1.8 times the charge, which you just calculated, was 6. And that gives you 10.8. This is the work done, so the unit of work or energy is joules. So 10.8 joules of work is done, or if you like, 10.8 joules of energy is supplied to drive 6 coulombs around that circuit in the 20 seconds that the circuit is open. That's how you use those 3 formulae. So let's think a little bit more about Ohm's law. We'll redraw the famous diagram. We have a battery sending a current through a resistance. The resistance is R, the battery has a voltage or a potential difference V, and we have a current I, and we know that V equals IR. Let's suppose that this is a variable voltage. In other words, I can change it, 2 volts, 3 volts, 4 volts, 5 volts, and so on. As I increase the voltage, since the resistance doesn't change, if the voltage increases, the current is going to increase. And if I plot a graph of voltage against current, for each of these voltages, every time I change the voltage, I put the ammeter in the circuit and I read the current. What I will find is I will get a series of results for voltage against current, and they will all be on a straight line, and that straight line will go through the origin. What is the slope of that line? Well, the slope of that line is simply the height of the triangle divided by the base. The height of the triangle is a measure of the volts. The base is a measure of current. So the gradient is V over I. But look at Ohm's law. From Ohm's law, you can see that resistance is V over I. So the gradient of the chart is just the resistance. So if you plot voltage against current, the gradient will give you the resistance. Now, having talked about Ohm's law, which is what this video is all about, I'm now going to talk to you about some devices that don't obey Ohm's law or don't always obey Ohm's law. Let's start with a basic filament lamp, whose symbol in an electronic circuit looks something like that. A filament lamp is the kind of light bulb that you put into the fitting in the ceiling to light up a room when you switch on the light. Now, the thing about that filament bulb is that it's got a very small filament in it, and as electricity flows through it, it gets hot. Indeed, it gets so hot that it becomes visibly hot. You get light coming from it, and of course it's that light which lights up the room. But it also gets hot. And the trouble is that as the temperature increases, so as temperature increases, that also means the resistance increases. Why? Because think back to the explanation of resistance. I said that the electrons are trying to get past all the atoms and molecules in the wire, and those atoms and molecules are not still, they're vibrating. Now, the hotter they get, the more they vibrate, the more energy they've got. And that makes it harder for the electrons to get through. So as the wire gets hotter, the electrons are impeded more, and that means the resistance increases as the temperature increases. So consequently, if the resistance increases, the current decreases for a given voltage. I mean, typically what you'll have in your house is the mains voltage, which we represent often by a little sort of symbol like that, and that's coming through your light bulb like that, and when you switch it on, it's cold, so it's got a low resistance, so it's got a high current. As it gets hotter, the resistance increases, so the current decreases, because V equals IR. But V doesn't change, that's just the voltage of your domestic supply. As R increases, I must decrease. So as it gets hotter, the resistance increases and the current flowing through it decreases. If we plot then a voltage current chart, you might expect from Ohm's law that you would get a straight line, but what you actually find you get is a line that curves up like this. What it means is that at a certain voltage, where you would expect by Ohm's law to get that level of current, you actually only get this level of current. It's a smaller current because the resistance has increased. And for most materials, it is true to say that as the temperature increases, so the resistance increases for the reasons I gave. But would you believe it, there is a device called a thermistor, which looks at the diagram form in a circuit is rather like resistance, except we put a line like that. That's a thermistor. And the point about a thermistor is that as the temperature goes up, the resistance comes down. So it's precisely the opposite of what you might expect. So if we draw a graph that shows resistance against temperature increasing in that direction, when the temperature is low, the resistance is high. When the temperature is high, the resistance is low, and it's not joined usually by a straight line, it's usually some kind of curve, smooth curve, not the one I've drawn. And so that just shows you that for a thermistor, depending on the temperature, the resistance will change. Thermistors are often used in temperature controls, for example, in the temperature control for your house, for your central heating. You would have a thermistor connected to some kind of logic device. We'll come on to logic and logic boards a little later on, so we won't worry too much about that now. But basically what that logic board would be doing is measuring the resistance of the thermistor. And what you would say is that whilst the temperature is low and the resistance is high, you want the central heating on. But as the temperature increases, when it gets to a particular point, which you could set on the wall, when the temperature gets to this level, the resistance gets to this level, then the logic circuit would say, once you've got to that point, switch the central heating off. And all the time you're above that point, all the time the temperature is higher than that, leave the central heating off. But as the temperature falls and the resistance increases, when it gets to a particular point, switch the central heating back on. There is another device that doesn't fully follow the Ohm's law, and that's called a diode. A diode has a picture that looks something like that. And the thing about a diode is it only allows current to flow in one direction. And the current, the conventional current, flows in the direction of the arrow, the kind of implied arrow here. If you try to send the current in the other direction, it won't flow. It's almost as though the diode has an infinite resistance in the wrong direction. So it will only allow current to flow in one direction. That can be very useful in circuits if you don't want currents to flow where they shouldn't. You simply put a diode in and it makes sure the current can only flow in one direction. Moreover, you'll find that you need at least a potential difference of 0.7 volts across that diode to get any current flow at all. Anything less than 0.7 volts and you won't get any current flow. So if we draw a voltage current chart for a diode, where this is the voltage, this end is the voltage in the correct way, and this is the voltage in the incorrect way, in other words, no current will flow, then what you find is if you put the voltage the wrong way round, you get no current. Even if you put the voltage the right way round, you still get no current up to 0.7 volts. But after 0.7 volts, you will get a current, and that will start to become, initially it's a bit of a curve, but then it's more likely to follow the Ohm's law pattern. That is a diode. You will all have encountered a light-emitting diode, whose symbol is something along the lines of this, the two arrows implying that light is being emitted. virtually every piece of electronic equipment that you've got, if you switch it on and you get a little red light coming on, or maybe a green light, or maybe an amber light, that's a light emitting diode. The current is flowing in one direction only, and it usually lights up to tell you that the device is on. Finally, let me tell you about the light dependent resistor. This is a resistor whose symbol looks something like this. This time the light is coming in. And the point about a light dependent resistor is the way it usually works is that the resistance will decrease as the amount of light increases. So this can be used to switch on a light when it gets dark. If you draw the graph of the resistance against light, this is dark, this is light, so we're getting lighter in this, getting lighter in this direction. When it's dark, the resistance is high. When it's light, the resistance is low. Once again, those are connected not by a straight line, but by a curve. But you could again attach this to some logic device that says that here you are in daylight, you measure the resistance of the light dependent resistor, and that resistance will increase as the end of the day comes and it's getting darker and darker, and you may set a particular point, say here, such that when the resistance reaches this height, you switch the outside light on so that it's light for when you come home. On the other hand, the following morning, as it gets lighter again, once you go past this resistance, it switches the light off.